welcome to the Cosmic Pie Podcast, episode number 35. I'm your host, Wayne Barkhouse, and with me today is
Robert Moore.
So we are streaming from the campus of the University of North Dakota here in Grand Forks. As always, we do have a chat that's running, so if you have any questions or comments you'd like to make during the podcast, feel free to use that feature. Also, as a disclaimer, Robert, we always have to have a disclaimer.
Always have to have the disclaimer.
The opinions expressed by Robert and I are not necessarily the opinions of the university, nor our Department of Arts and Science, of Physics and Astrophysics, nor the College of Arts and Science, nor the governor from the North Dakota, the President of the United States, the head of the UN, you name it. It's only our personal
opinions.
So if you have anyone to blame or you don't like what we see, you know who to target, right?
That's it.
Target Robert.
Target me. I'll take the blame.
So, Robert, we do have a special guest today.
Yep. We have a special guest. This is Dr. Angelle Tanner. She is at the Mississippi State University. I met her at Georgia State University many years ago now. And I'll let you introduce yourself further.
Okay. Well, I'm an associate professor here at Mississippi State, and I'm an astronomer. And I've been specializing pretty much since I got my PhD in the study, detection, and characterization of extrasolar planets.
All right. So, I didn't think to ask you before we started out what you had planned to talk about.
You did over the internet.
Yeah.
We can talk anything. I've been excited about JWST results. There's been some interesting exoplanet things happening. I used to study the black hole at the center of the galaxy, and then I wore my alien shirt today, so I'm game for lots of things.
All right.
So, Robert, we did notice that there was a result that just came out yesterday. And maybe we can get some more in-depth information about this.
Shall I call up the slide on that
Sure.
first? Okay.
If you want to describe what we're seeing here.
So we had space.com had their headline of James Webb Space Telescope detects quartz crystals in an exoplanet atmosphere. And so this was around WASP 17b, which is a hot Jupiter, if I'm remembering correctly, correct?
Yeah. So some of the data, for those who are interested, so the surface temperature of this exoplanet is estimated to be on the order of about 2,700 Fahrenheit.
Oh, wow. Yeah, that's a little warm.
It takes about 3.7 days to go around the host star once, and the host star is at a distance of about 1,300 light years from us. Now, in terms of mass and size, it's about roughly half the mass of Jupiter, but because it's so hot, it's expanded outwards, of course.
Right.
And is almost twice the radius of Jupiter in size. But the very interesting thing in all of this, if you want to show the next slide, is the spectrum that was measured by JWST, which points to the fact that there might be what in its atmosphere, Robert?
Might be SiO2, silicon dioxide. And so, Angelle, I'm showing the slide of that composition, that spectra, and with the data points and everything.
Yeah, I'm looking at it right now on the press release site.
Okay. So, again, I will point out that what we're always looking for is spectra. And that's the fingerprints of the silicon quartz is impressed upon the light and the colors of light that the planet is absorbing and emitting. So, anything you want to add?
Well, so these particular systems are super exciting because they're transiting systems. So the planet will travel along its orbit and go in between us and its host star. So it's because of this transit that we're able to analyze the atmosphere and study the composition of the atmosphere of the planet. So I wish all planets did this, but they don't.
Right.
And JWST, this is one of the reasons it was designed to do this. And this is one of many new results we can expect to see similar to this. It doesn't make for very interesting, pretty pictures, unfortunately. That was especially true with the WASP 39 result.
Right.
When the thing was first launched. you saw those pretty pictures coming on in Times Square, and then the little squiggly line showed up for exoplanets, but that's okay. But this is still, yeah, I know, but this is still interesting. I mean, there's a lot of stuff. I'm not an atmosphere expert by any means, but yeah, I think this is one of the first times we've detected this particular. I don't think I've ever seen us detecting definitely quartz crystals, so that's pretty cool.
Yeah. And I'll throw in there, using my background with the planetary and the geosciences, yes, SiO2 is quartz.
Yeah.
And so this is literally that at 2700 Fahrenheit, quartz has been melted and vaporized on the surface, launched up into the atmosphere where it cools, and recrystallized into quartz.
Okay.
And that's what's being picked up is in about the 8 to 9 micron wavelength of infrared. They're picking up emission lines from hot quartz.
Yeah, and this is not a planet you would really stand on the surface of. This is more something like, Saturn, Jupiter, as we call it, a hot Jupiter.
Right.
So it is kind of a lot of times people think they envision themselves standing on the surface of something, especially the way the press releases are written. Enjoying quartz rain, but that would be what kills you. The pressure of the atmosphere, but yeah.
And the temperature, yeah.
Yeah, just
And the temperature, the 27 Fahrenheit.
just to point out for people who are looking at this who are not familiar with this type of research, is you see the spectrum that's in the foreground, but in the background it's like a part of a planet. That planet is just an artist's conception. It is not the
Right.
image of the planet
Yeah.
itself.
Thank you. That's another misconception. We have such good artists that they make really good.
They make
cartoons.
really good cartoons.
Yeah.
And people think that, that's the picture they took. No, the picture of this planet would look like a little dot of light next to another dot of light.
And the quartz crystals being in the atmosphere is not the result of wind blowing on the surface of a desert, somehow transporting that material up into the upper atmosphere.
Right. Well,
But Robert's analogy was true. It probably is getting lofted
mhm.
in some way.
It is some way getting lofted, but at 2700, I'm forgetting what the melting point of quartz was,
Oh, okay.
which is really bad of me because a large part of my research at Case Western was involving melting silicate material.
Melting
But-
point of quartz.
So she's looking it up.
I
Yay!
have the internet. You guys have all your hardware to keep track of. I don't.
Right. So anyway, yeah, it's either being directly melted and vaporized, or there are some really strong winds, and I'm betting on a little of both. So
Scientists Celsius. Put it in
Oh.
Fahrenheit.
Well, it's interesting from the point of view of why this planet and why quartz crystals. Like, where does it come from? Why don't we see in other planets? So it's sort of some generic thing related to the particular environment that we have at this particular exoplanet, right? That's going
Right.
to create this sort of ingredients, right? If you like, the signature in the spectrum.
right. Well, I mean, it definitely points to, no matter how it got up there in the atmosphere, it points to there being a solid rocky surface somewhere in that planet. Because most of your rocks, by the way, are also made out of silicon dioxide. They're
Right.
quartz.
So it's not going to be like Jupiter and Saturn in that sense, right?
Right.
Because maybe there's metallic core in those planets, but it's not a
Right,
surface
right.
you're going to stand on. If you could survive the pressures and the temperature, they may be a rocky surface
on this one.
on
Yeah.
this one.
Yeah.
Okay.
Because yeah, Jupiter nor Saturn show any signs of silicates in their atmospheres, but they're also not 2700 degrees.
So it's one of the questions I have that's not related to the JWST observations that we just showed is, the first exoplanets that were discovered are actually not going around normal stars, as we'd say, but going around a neutron star in a pulsar system. Has anyone ever figured out, and it's to my recollection, I think we discovered exoplanets in one other pulsar and that's it, and literally we know of thousands of pulsars. So, and there's lots of targets we can look at in detail for the timing of the arrival of the pulsar signal to try to infer the presence of little tugs, if you like, from exoplanets going around them. Has anyone ever come up with a reasonable explanation of why there would be planets around an object which is a remnant of a supernova explosion?
I know I have been surprised that we haven't found a lot more of the systems, because I'm Googling. There still is only a handful of known pulsar planets. I think it's 1, 2, 3, 4, 5, 6. I think the papers that have been written about it is they think that maybe either these are the leftover cores that managed to survive of the planets after the supernova explosion, or it could be material that recoagulated from the debris left over after the explosion. Because I know that planet recycling has been, or second generation planets have been discussed since the discovery of some of these planets. Because they've been also suggesting that that could even happen in a place like the solar system, like when the sun turns into a red giant and vaporizes all of us, and then once it calms down and turns into a white dwarf, maybe some of that leftover material could recollapse and form a different type of solar system. But I haven't read too much into it about where they come from yet.
Now, one of the things that comes to my mind right away is I wonder, because we can kind of age a bit pulsars, right? Looking at how fast they're rotating, the fastest one without any interference, the millisecond type pulsars presumably could be the youngest ones, and as time goes on, they would slow down through the release of energy from the system. That I wonder if we could use the actual, rotation of the neutron star as a way to age the system. In other words, we could see, do these planetary systems only show up with pulsars that have long periods rather than ones that have short periods, giving us some constraint on how long it takes to actually form these second generation of planets, if you like.
Yep.
That's a good idea. Unfortunately, there's no, let's see, I'm counting the number of planets, but there's only 1, 2, 3, 4 systems. So as always, we scientists, we like more data.
Right.
So that's hard to, and I'm looking at Wikipedia. So I don't see anything about, ironic. That's a whole different discussion, which we could have today.
Yeah.
About the fact that Wikipedia is where I have to look to find this information quickly.
Well, that's what it's good for. It's quick.
I know. It may reflect the existence of asteroid belts around the pulsars. So yeah, so this is definitely maybe one of the sources of the planet.
Well, then that begs the question: out of the thousands of pulsars that we know, why is it only a handful?
Why is it only 4 or 5?
That is true.
But the thing to me, this begs the question of just how fast do planets form?
Right.
Because the last I saw, we were finding out that they have to form in like 60 million years after the star hitting the main sequence. Because,
some of them are like 10 to 20 million years, I think.
Oh, wow. So even faster.
We're still figuring this out. I mean, this is part of the research that I've been working on. We need to find more planets around young stars. I mean, this is stuff that Russell has been working on forever. And he's actually found a couple in the Beehive cluster, which I thought was cool.
Yep.
Russell is Robert's old advisor.
Right. I was about to comment on that.
An old friend of mine. I went to grad school with him, so I've known him forever. But again, statistics. So we're just now being able to find more planets around young stars. Unfortunately, young stars are a pain to find planets around, at least with the radial velocity method, which is what I use, because the stars themselves are more active. They have flares and star spots and stuff, and that messes up our observations. So we've had to go to the infrared to look for them. And so we're kind of catching up with the stars that we're used to around, stars of the sun.
Now, for those who don't know, could you maybe define what you mean by radial velocity method?
Yes. So the radial velocity method, also known as the Doppler method, is where we look at the star itself, and so when the planet is orbiting the star, gravity is at play, and so the star will actually wobble due to the orbit of an unseen planet. And so some of the very first, depend on who you ask, it could be pulsar planets, but in 1989 we actually did discover a wobble of a star due to an unseen planet. We didn't know what we were looking at first. But as the star goes towards you and away from you and towards you and away from you, because of the planet orbiting around, that's what we're detecting, that Doppler shift.
Okay. And Go ahead.
So I'm just going to mention, so in other words, you just to kind of go down a little bit of a rabbit hole, you get down to the talking about life elsewhere, and some people go down this argument, oh, we got to be quiet, we don't want to broadcast messages purposely with a radio telescope out in the deep space. You never know what life form might pick up that signal and maybe come to Earth to investigate. But just the fact that our sun has a system of planets, you can't hide that, because if we can detect planets going around other stars, they can clearly detect planets going around our own sun, including the Earth.
Right.
Yeah, and someone recently, I think Jackie Faraday over at the Museum of Natural History in New York just published some sort of paper about the number of systems for which the Earth is transiting. So if you think about it the other way, we're looking at transiting systems. Now flip it around. How many stars in our local neighborhood would see the Earth transit our sun? That's another thing to think about, as far as you can get even more information. If there is the same intelligence as us, which odds are that's not going to happen either plus or minus a million years. But yeah, so we're definitely, it is going to be no secret that we're here. So I don't really worry about that.
And I guess to do that line of sight analysis, I mean, you probably do that now with Gaia mission, right, with the data.
Well, we're doing it right now with TESS, yeah. So we have the ability. That was the whole point of the TESS mission. TESS, I always forget what it's for. The exoplanet survey satellite. I forgot if I get that wrong. I mean, we are building missions specifically to look for Earth-sized planets in the habitable zone of solar-type stars.
Right.
So we are zeroing in. Kepler was supposed to do that a little bit. TESS is doing an all-sky survey.
Okay.
So yeah, we are currently looking for those types of planets.
Right, but for another planet to see us as transiting in front of our sun, then we got to know the exact alignment. That's kind of what I was thinking in terms of Gaia, because now we know more accurately the position.
Oh.
Yeah, that's what I was referring to. Yeah.
I don't remember what she used. I'd have to go check.
Okay.
I Googled. That's too hard to Google at the moment.
Yeah, that's
Think about the title.
Yeah, and so there's no way to hide. I mean, even our signals, obviously, as you know, the techno signature, as they'd say nowadays, right, is out there for everybody or anything to pick
because
up.
I'm going to sit here and point out we're looking for chlorofluorocarbons in the atmosphere as an indicator of a technological society, because there's no other way to put those in there. And we're broadcasting that information, if nothing else. So, yeah.
Well, hopefully they can't detect a hole in our ozone layer.
Right.
Hey, I thought it filled up a little bit.
It did, but it's still there.
It's still there.
I heard that it might be coming back. Lord knows we're going the wrong direction for all this.
Yeah, exactly.
Oh, here we go. I found the paper. Oh, that was Nature. Okay, I didn't realize. Past, present, and future stars that can see Earth as a transiting exoplanet.
There we go. Cool. So
1,700 stars within 100 parsecs. Convert that into light years. That's a lot of stars.
That's a lot of stars.
Yeah, that's like what 326 light years.
Yeah.
So
that's a lot of stars.
Yeah, and you think of the EM signature from the Earth, that's what, roughly 100 years old, let's say at the earliest. Right. So we're about 1/3 roughly that distance, right? So.
Yeah, I still point out though that that limit, at the 100 light year limit, the signal is going to be so weak that it's going to get lost in the background noise.
Yeah, well, isn't there interstellar scintillation effects too? You have to worry about that, right? So
and now we're going down a rabbit hole.
Yeah. Well, I mean, it's ISM, right? The way to think about it is that our Milky Way is not clear of dust and gas.
Right.
So you can think of the Gaia mission, which is, we had mentioned this on a previous podcast, which is a European Space Agency mission to measure the small shifts in the position of stars to give us a way of measuring distance indirectly to those stars.
Right.
That if you look at just how precise its instrument is, it can literally see out to 100,000 parsecs, which means really the whole Milky Way.
That's the whole Milky Way.
But it can't do that, because therefore it'd be able to see every star, because there's lots of gas and dust in our Milky Way blocking the view, right? So
that's why we see spiral arms. That's why there's a dark streak through the middle of the Milky Way. If you're dark enough sky, then you can see.
But we're happy for that material, right? We're not cursing it, because that's where we come from. We wouldn't be here if it wasn't for that material.
For that dust. Yeah. Yeah. So, shoot, where did I go from there?
No, I just want, so can you maybe describe some of the recent research that you've been doing, some of the exciting things that you guys are working on?
Yeah, a lot of things going on. I did want to point out, if you guys have discussed that, back to the rabbit hole, that technosignatures are really finally being considered a research area.
Right.
Again, by NASA. We've actually had, I went to a AAS, American Astronomical Society meeting, and where they were talking about technosignatures. So it's been a while since we'd seen that. I didn't understand any of the talks because it all had to do with radio data.
Right.
Signal, it's still signal analysis, but this
Right.
is, I do like aliens.
Well, just to stop you there, so when you say that it's being noticeable, I guess, to paraphrase you, to me that means to me that means funding, right?
Yes, so it is. Yes, but yes, and not laughed at.
And not laughed at.
30 years ago. I mean,
Yeah.
I think Joe Tarr would be very excited about that.
I-
Yeah, taken seriously. I mean,
Yeah.
again, if you don't look, you're not going to find anything.
Right.
Right. I mean, we always impress on students and others that you propose for funding from NASA or a National Science Foundation and stuff, that you want to come up with novel ideas. But if they're too novel, you're not going to get funded anyways.
You're not going to get funding.
And
Yeah.
there's been discussions. I have been present in discussions where we've had that discussion where it's like, where is the space for that novel, they call it high risk, high reward studies. So this is something that does get discussed on these panels, and it is a problem because of the funding nature, the funding
Right.
environment that we're in right now.
Yeah, and I could think of maybe even private funders would be more apt to support that type of high risk stuff, right?
Right.
Rather than the government itself, because it is giving people researchers the people's money, right? In that
Right.
sense, so it has to watch out for that, right?
Yeah, I mean, we all know about the breakthrough program with Starshot and Listen and all that stuff, but
Exactly.
careful
And
where that money.
And there's always a group out there that says, "You believe the NSF funded this? It's how do crickets snore?" All these topics they come up with. Right?
I remember a congressman getting upset because some of the funding went to funding a trip to Africa to study the social behavior of a certain species of ant. And he was just all livid about what use is that? And it's like,
And that ant could only be found in Africa, right?
right.
So you had to go there to do that. But you can think of the SETI program, right?
right.
So that was cut
Well,
off by the politicians
and
too
I-
at one point for NASA.
Yeah. And they've got one of the largest radio and microwave arrays. So they're perfectly set up to look for these hydrocarbons, these technosignatures, because a lot of their spectral lines are in the microwave and radio wavelengths.
Right.
So
Yeah, a lot of it's just we as scientists don't always do a good job of explaining why we do what we do
right.
to people, and that's always been a topic. I remember when McCain ran for president, at some point someone complained from his area of things, because I liked McCain. I mean, I'm not conservative, but McCain was pretty cool. About the volcano monitoring, like in Hawaii or something, and why is this a thing? And I'm like, really? You didn't think to kind of check that volcanoes can actually bring down airplanes? I mean, that's
Right.
actually a fairly big topic that might sound like it's silly to you, but if you had a little bit of time to look into it, that was a very important study.
Right.
They
Well,
completely airplane travel.
Oddly enough, that's a circle back to an earlier topic, the melting point of silica, because a lot of the volcanic material that's blown up is silicates. And their jet engines are hot enough to melt them, and so you turn your jet engine that flies through it into a spun glass factory.
Oh, that's what I looked at it. And the melting point is about 3,000 degrees Fahrenheit.
Okay.
Converted.
So, yeah, you get. This is why we study this stuff, and even if it's not that important, the stuff we learn to test for it
Right.
can lead to all kinds of, real world benefits.
Well,
So,
that's the thing that gets me is not funding the basic research and development type of things, right? You could think, because right away someone will like, what are you doing? Oh, so you explain to them what you're doing, studying, let's say, exoplanets. How's that going to make gasoline cheaper? Because they want to see the direct benefit, right?
Right.
Yeah.
And it's like a lot of times, this benefit could be down the line because it could involve the development of, technology that ultimately may lead to exploration of looking for oil and then cheaper gas in the future. I mean, who knows, right? But the thing you point to right away is, you'd say the same thing probably about Einstein and general theory and the special theory of relativity. Yet, where are you now without your GPS system today?
Right.
And
Well,
that,
I often emphasize, like I just had, 5 undergrads in my office a few minutes ago, and I'm using astronomy for exoplanets as a way to get them to learn Python, computing language that I'm sure Robert's really excited about right now because he's taking a class.
Yeah.
right.
Oh, yeah.
Just the fact that I'm helping them become excited about a computing language is going to help them in STEM. And, they're going to go off and I don't know what they're going to do, but just, you have to start somewhere.
Right.
Right.
And this has actually been a really big topic. I'm glad this is an hour-long show because I'm in Mississippi right now.
Right.
My thoughts are my own, I should say, not Mississippi State. And there was some politician somewhere who's now saying that like we should get rid of all the humanities and all this stuff. We only should have majors that lead to high, that make money. So
Right.
ironically, that is STEM. But then I'm like, well, first the English department had a bit of a fit, obviously. And not everybody's cut out to be a STEM major. So that was my first reaction.
Right.
Was this, listen, dude.
And most lawyers or doctors don't end up majoring in STEM disciplines before going on to med school or something like that.
No.
So yeah, I remember now that him getting up on his soapbox to preach, the only majors that should be being offered are these that lead to high paying jobs. And it's like, you can't know that.
Well, I take a much broader kind of viewpoint right away when someone mentions that, is the fact that what worth is society if you don't go into all these different areas and disciplines like the arts and culture and all that. That's what makes society worth preserving, is
Right.
everything together, not just one single aspect of how do I make a fast dollar or how do I become rich and sort
Right.
of thing. So to preserve society, which we
Not
want to do, you need everything, right? I mean, it's
I'm
just,
still not.
yeah. And how you gonna write papers if you don't know how to write, period, right?
Right.
Without taking English of any type.
They're not. Their writing is not getting much better, especially now with the advent of AI. We're kind of worried about that.
Yes. That's a whole nother topic though. But yeah, AI has a lot of people upset and wondering, and
Yeah.
a lot of it is coming also from not just its use, but how do you train it?
Right.
And
But it's interesting when you mentioned about Python and using exoplanet data to help develop Python programming skills. I'm just visualizing, if I could get into my DeLorean and do 88 miles an hour. So I just told you how old I am. And I go back in time to, let's say, 1980. And I tell people, if they ask me, what are you doing where you are in 2023? Well, we're using exoplanet data to allow students to, learn Python computer programming. You're doing what? There are exoplanets? That would be such a shock, right? So it's kind of funny how things change in a relatively short period of time.
yes.
Yeah,
But-
I wish I could get in that time machine and go in the future.
Yeah.
Yeah.
If I could be an undergrad right now when yeah.
We're doing
exactly.
so many interesting things right now with the Europa Clipper and all these other missions that are coming up. I'm jealous of the people in undergrad right now because
Yeah.
amazing things are coming.
Imagine like 500 years from now, assuming we don't destroy ourselves, and we put more energy and effort into exploring our solar system, what we could be doing.
Right.
Yep.
And that's the whole point, folks. Yeah. As Angelle said earlier, we don't always do well as scientists on presenting these ideas and getting them out there. Why what we're doing is important. So
Yeah, and that's
Yeah, and that's why
yeah.
the AAS, we actually do send astronomers to Capitol Hill at
Oh,
least once a
cool.
year. It's usually in March. I haven't done that yet.
Do they really do they listen? I mean, it's one thing to send people,
Well,
but
as usual, it's probably a staffer, and it depends. Um, I I I don't know if they listen, but I think it also trains the astronomer how to talk to the staffers.
right.
Uh, and that's something that was fairly obvious because there's two astronomers in Mississippi, and so that's one. I always joke that's one per senator. I've always thought about that when I first moved here. Now we used to have a semi-cool senator, Thad Cochran, who he died of something with his about the same time as McCain did. But he
Yes.
was definitely very pro-research. I don't know if he was around when you were here.
He was.
Robert.
He was.
Yeah, he was super pro-research. Like our research area is called the Thad Cochran Research Area.
Oh, nice. Okay.
He would have been someone that I would have been happy to go talk to, her staffers. But now the two senators, they're scary. Like climate denier kind of types. But no, Thad was actually pretty cool about research. And he realized that it was a good way to bring money into the state. He understood the economic connection.
Right.
Yeah, they keep complaining about brain pain, and I'm like, that's not lack of STEM majors is not why you have a brain pain.
Right.
yeah, I mean, even for when you're talking about science literacy, it doesn't really matter which political side you're on in some sense. So if you're on people who think that the environment is the number one thing we have to be looking at, you need science to figure this out, atmospheric science, so on and so forth. If you're on the other side of things and you're a climate, denier, if you like, to use your words, then a lot of times those people are involved in other things that you need science in, like whether it's the military or something, right? How are you going to do all this other stuff? It all boils down to having science literacy as being a strong sort of foundation in whatever society you live in, and we see the benefits, both
Right.
positive and negative, of course. And we want to, of course, try to just go with the positive side of things.
Well, I would think that if whichever side you fall on, you'd want evidence brought forward to show your side. So how are you going to do that without somebody out there doing the research?
That's it. And that's why I like space exploration, because if that doesn't motivate you, right? If you can't
Mhm.
motivate the neighbor, then you're not explaining to them appropriately, right? You need to do a better job because it's so exciting. And once you explain to them what's going on, maybe they'll get excited as well and support that part of life. At least space exploration, we're not going down this rabbit hole of killing people and doing harm. It's one of the most peaceful things we can think of.
Right.
Most cases.
Most cases.
Yeah.
Uh,
But anyway, so getting back to the exoplanets and stuff, so one of the things we like to do, of course, as you mentioned this already, is to try to find Earth 2, if you like. That's kind of a push there. But of all the exoplanets, and there's been a large number of them, and you can maybe mention what the latest numbers is, how does the Earth fit in with those type of planets? Now, I know there's things we have to look at, like what truly is, if you could examine the solar system of all these different, 10,000 stars, you get some statistics on what the planets are like. But then we have to worry that our detection methods are biased in detecting certain types of planets and may not so well detect others. So how does the Earth fit in with the type of exoplanets that we know that exist so far today?
Well, if my dog would stop licking me, I would look up.
So here's a question. Are there any exoplanets that have canines besides the
maybe,
Earth?
I
maybe.
was going to say around Sirius. All right.
Right, the dog star.
For those that don't
Right.
know, Sirius is also known as the dog star.
Right.
I went and looked at the NASA Exoplanet Archive, which is actually a pretty good site. And right now the current count is 5,528 confirmed exoplanets. Now, what's strange about the Earth, and you're right, so some of it's a detection bias in that we've only become sensitive to Earth-like planets orbiting sun-like stars kind of recently. But we're just now starting to notice it's been like 30 years that we've been doing radial velocity surveys, maybe 40, time flies. And we're finally getting enough data that we are sort of seeing that the solar system with its 4 inner terrestrial planets and 4 outer gas planets is not terribly common. So that is currently something that is definitely being discussed. Is the basic architecture of our solar system unique compared to what we're seeing out there? And right now, some hints think it's unique. I'm trying to, again, stop looking at me. I'm trying to look at a plot. Yeah, so we're definitely kind of, but we still need to fill in the data a lot more, because we're just now starting to be able to detect systems like our own.
Right.
It'll be interesting when the Gaia, we're all waiting for the Gaia data to come out, although it's not as sensitive as we would like, for the astrometry data to come out. So that'll be in another couple of years. They're still crunching the data. We'll detect a whole bunch of planets that way.
Okay.
Yeah, I think there was a release, wasn't one due this month, October, but it's not it's not all
Yeah, no, it wasn't the planet
yeah.
one. It's a bunch of ancillary data.
Now the other thing, when you think about the Earth and stuff, you kind of wonder, some people are looking, did you ever read the book, what's it called? It's about, I'm trying to think of the title, Peter Ward, his book about Earth being isolated, alone, like one.
Oh.
I forget the title of the book.
I don't know.
So he went through him. I don't know if you know what book I'm talking about. Yeah. So the argument basically was, or is, I should say, that there are a lot of factors that need to go into the recipe for the reason why life has evolved to the intelligent it is today.
Right.
That we've gone through all these different things, including surviving, the dinosaurs. Think of the mammals.
That's the weird thing for me, is the whole what would be here if the asteroid hadn't hit. I mean, that was just such a freak accident.
Yeah.
Right.
Yeah. And then Jupiter needs to be there because it needs to clear out some of the larger asteroids early on, so we don't get completely bombarded,
clobbered,
all the time, where life gets going, then all of a sudden it's gone again, right? Because of that. So there are a lot, and the fact that we have a moon would stabilize the rotation, the tilt of the Earth's axis,
Right.
all these kind of things. So when you actually boil it down, the probability of intelligent life as we know it here on the Earth to arise is like it almost would happen only once in the observable universe, from the point of view of statistics only. And so if our solar system is on in the minority side, one would wonder what impact that would have for the rise of intelligent life elsewhere.
Right.
Yeah, and it's such a complex problem. It's just very hard to model.
Right.
Yeah.
Well, I always point out, because it was an interesting fact for the moment that I was a psychology major, in a biological psychology class, they pointed out that your brain takes up 1/3 of your calorie intake just to run it. And so the point was made that unless intelligence gives you a strong survival advantage, it's not going to develop.
Yeah. That book I was referring to, by the way, is called Rare Earth by Peter Ward and Donald Brownlee.
Okay. And I noticed we've had a question, so I'll throw it out to the two of you. Will JWST be looking at the Bootes void or other voids?
Oh, goodness gracious. What a very specific question.
Yeah.
I'm going to Google JWST.
Voids.
Yeah, the answer is yes.
The answer is
yeah.
Okay.
Because one of the primary goals of JWST is to survey galaxies.
Okay.
Cosmology. In fact, the early funding from JWST that I understand it was a push to look at very high redshift stuff, right? Which is why it was built to be sensitive to the infrared. And some people argue, well, what about stellar astronomers? Well, if you're sensitive to the infrared, you can also look at star formation and all these other things, right? That happens near space, right?
The Bott globule. I would have known what that was. I didn't realize that was called the Bootes void. I always showed that in class.
Okay.
Yeah, so the Bootes void, that was done way back by, I haven't seen the names. It was by Bob Kirshner, way back. He was part of that survey back in the 1980s, where they did these pencil beam surveys. So looking at very small area of the sky and just going as deep as possible. And they found a region, and when you probe a sightline through, which had a very low density of number of galaxies. So now with large-scale structure, like data that we get from the Sloan Digital Sky Survey and others, we have these large areas on the sky which have low density of galaxy, like 1/10 the density of outside of those voids area. They're the interior bubbles of the large scale structures, the way of thinking.
Oh,
Okay.
this is not what the Bootes void is. Okay, this is the downside of the internet.
Yeah.
Something that said it was the. Okay, sorry. This is an extragalactic thing, folks. I'm not an extragalactic astronomer.
Yeah, so one of the big push in the last couple of years is by Jim Peebles, who won the Nobel Prize
I
recently.
know that name.
Yeah.
Yeah.
So his push is to get observers to look at galaxies that are in the void and see if there's anything different about them than galaxies that would populate the filaments, the walls of the bubbles type of stuff. And as far as I know, I don't think there's really a big difference that has been discovered, but JWST will certainly be looking in those regions. You want to look for example, there's a big push to look for dark galaxies, and these would be galaxies that don't have a lot of star formation going on. So for whatever reason, the formation of these massive luminous stars have been truncated for whatever reason.
Right.
Or that maybe they're very dusty, right? So a lot of light gets absorbed by dust and re-radiated out into the infrared. Then JWST would be able to detect those easily, right?
Okay.
That's the kind of work I think they're looking at.
Okay.
I now
Cool.
see the picture of it. That makes much more sense. I just covered this in I just covered large scale structure in my astronomy class.
Yeah.
All right.
I get all excited about, I was a postdoc at the same time as Jane Rigby at Caltech, and I'm a big fan of hers. And I get all excited about these little red galaxies and just JWST, even though I'm not a galactic person, is just seeing all these galaxies that they're already confused as to why they're there already. Because like one of them they think it's only 100 million years old, and they're still trying to figure out how you get something as massive as the Milky Way after 100 million years, and all this really amazing stuff that, again, JWST was built to do.
Right.
Yeah, and I could actually tie that together with what we had talked about previously, and that tie-in, as Robert and I had a good discussion on previous podcasts about this, is that this thing of finding massive early galaxies doesn't really necessarily means that the Big Bang Theory is now null and void, but it means that we need a better understanding of galaxy formation. Things can happen or form a lot faster than what we thought of. As you think of standard gravitational collapse, maybe that also would affect the formation of planetary systems.
Right.
Right. So I didn't realize that it was these massive galaxies, because I completely ignored the stuff about the Big Bang stuff being null and void, because I knew that was not a thing. Yeah.
Right. Even though Michio Kaku and a few others are
Yeah,
saying
he's
that's
the
exactly
last
what it is.
person I would talk to about anything. Don't be excited about Michio.
Okay.
Particle physicist, not a cosmologist.
Right.
Anyway, yeah, I didn't realize that that's what was going on there. So, and that's happened before, right? I mean, I told my students for a while there, we had a Hubble constant that disagreed with the ages of the stars in globular clusters. And it didn't mean that everybody was wrong and, oh my God, we're idiots. It meant that you had to go fiddle with the Hubble constant in one end, and you had to go fiddle with the way we were modeling the globular clusters and getting the ages of those stars. So it's all about the scientific process.
Well, even in the 1990s, to bring that up even to more modern times, if you like, was the fact that we were finding that the ages of globular clusters were older than the universe, but we were missing the presence of dark energy. And once you add the dark energy, that lowered, right? That increased the age of the universe from 10 billion to be the 13.8 we know it is today, or we think it is. And that all of a sudden, the universe was older than the globular cluster. So your mother is now older than you are.
Right.
In that sense, right?
I think some of the ages for the globs, well, maybe that helped them narrow it down, but I wasn't paying attention to that part of it.
Yeah, because I remember, I'm from Canada, which I am, and I studied at University of Toronto, did my PhD. That's historically a globular cluster haven for research, right? So I've done a lot of work in globular clusters and seen others do work in that. And so the age data they were getting from globular clusters, there's not a lot of wiggle room.
Oh,
Right.
okay.
And you can't really change, down to the stellar models. You think of the solar model because you had helioseismology to constrain those parameters. So you could, like Pierre Demarque and others, at Yale couldn't do a lot with that. You were really tightly forced into this little funnel area of parameters you can adjust. And so when they came out with, for example, the dark energy now, the time, this also relates to get off now, another rabbit hole, the fact that we were detecting 1/3 the number of neutrinos coming from the sun. So the solar neutrino problem, was it that we didn't understand neutrinos, or were our solar models completely wrong? Once again, there was not a lot you can adjust in the solar models, and it turns out it was the mixing of the different types of neutrinos that was the answer to it. You see, so yeah.
Thinking about a bunch of stellar theorists or stellar modelers trying to convince cosmologists they're wrong.
Yeah.
Right. And that's, a big thing is, like the scientist we won't mention again. He's not a cosmologist. So while he knows some of cosmology, a little bit, he's not qualified to make any comments about what we know about cosmology, and that's something else.
Not the science guy either. I mean,
right?
I do. I'm a fan of his. I actually do like Bill,
but
yeah,
you don't go to him for cosmology, So,
but it's nice to have check and balances. That's how science is supposed to work. To me, it's like a random walk, right? Where eventually you're getting to where you need to go as the ultimate truth in something. But you can certainly go down wrong ways, blind alleys, and have to, correct the course of your ship, right? Because of new information that comes along.
Right.
And that's science, right? So when the public thinks that, oh, you scientists, every word you say has to be exactly, the truth, that's not the case, right? We do a lot of work in consensus, right? The majority opinion is so and so and so based on this fact, and this fact. And in fact, it always brings up, and it's hitting my mind to think about it, the use of the word theory. That has been now turned upside down, right? From the point of view of science, when I say I have a theory of something, that means I have some facts, some evidence, whether it's observation, experimental, or both, that supports the idea I put forward. If I didn't, it would be a hypothesis. But when someone in the general public talk about theory, like, oh, that's just a theory. It's not just because that means a theory has all of these facts that support it, right?
Right.
And so that word has been twisted in the English language.
I've tried pointing out to people that if you start talking about science and you go, oh, well, it's just a theory, you just admitted you know nothing about what you're talking about.
Yeah, and it's when you're mentioning the English language, I've been grappling with this a lot because language matters.
Right.
And one of the things I've been working on is trying to get data access and open data and making data more accessible. And literally telling people at NASA to quit using acronyms as much as they do, when talking to people, and making the language in some of these proposal calls that they do, I know they have to speak NASA-ese, and legalese actually is what they're calling it. But the language they use is really a barrier to people understanding what the heck they're asking for.
Right.
It's not just been me. I mean, I've sent text to experts in the field and they couldn't figure out what NASA was asking.
Right.
So language matters. And the things that we call things matter. And,
right.
And the theory, yes. And yes, certain groups tend to take our words and throw them back at us. The word woke has been completely destroyed. But yeah, theory is a good one too, where we don't understand. We need to start teaching that, hopefully at the K through 12 level, make sure everybody understands the difference.
Right. Well, at the K through 12 level, I got to admit, I was once taught that a theory was an educated guess. And looking back now, that was the most horrible thing that could be done, because all people are going to take away from that is guess.
Yeah, guessing, exactly.
And it's like, that's not what a scientific theory is at all. It's not a guess. It's backed up by observations and experiment,
Yeah, and then James points out some of the issues of how science is depicted in the media and in popular fiction, and that's exactly right.
Right.
I mean, if you think of getting to the masses, right, if you alter things in a way that's not reality, not how it's really done, in practice, they're going to get this notion that is how it's done.
Right.
And so that's a big problem.
In the movies, you get a biologist who suddenly knows about how to deflect an asteroid. And it's like, no, they don't. They have no idea.
Have you guys ever owned a lab coat? I think I got one for Halloween once.
Right. I have one, but it's for my union I belong to. Evil Geniuses for a Better Tomorrow.
You mean we don't send... You mean we
Unless
don't...
it's cosplay. Yes, cosplay.
I mean, we can't send Bruce Willis off to an asteroid to drill...
Drill a hole? Yeah. Yeah. And you can always train drillers to be astronauts faster than you can train astronauts to be drillers, right?
That is true. I don't know. Those astronauts are pretty smart and they're in really good shape. So
Right.
Well, you think of most of the hours on that journey is going to be doing astronaut-like things rather than drilling, right?
Right.
So.
flip the switch. We need to flip this switch at 0800 hours. Not kill each other along the way.
Going back a little bit, though, I'm going to have to say you'll pry acronyms from NASA when it's their cold, dead fingers.
I know. It's a military. I have one of my students. Her family is military, and we definitely bond over that. It's the military heritage, and again, not wanting to say a really long term. Whenever you need to say things quickly, sometimes using an acronym is appropriate. So
Right.
Yeah, and you think of, like you mentioned about proposals, right? There's a lot of desire, if you like, to bring in more people under the umbrella to do cross-discipline type of connections, research, or public outreach, and so on. But if you're trapped in this narrow-minded view of these acronyms, it's hard to bring outsiders in on that. They got to learn all of this stuff and
Right.
so on. Right? So.
yeah, I was just at a meeting in Boulder where we were discussing. It was a bunch of different NASA divisions. I'm not at NASA, and they were discussing repositories, which is their word for archives. But I couldn't understand most of what they were talking about, and it was ironic because the whole point of the meeting was to encourage cross-disciplinary work and to do open science. And I had to raise my hand a few times and go, I don't know what you're talking about because you're using language that I'm not familiar with. And even if they had a little cheat sheet, that would have been handy. But at some point, one of the guys is like, well, and according to my VIP, and I'm like, what is a VIP? And he's like, well, how do you not know what a VIP is? And I'm like, because I don't work at NASA. And it was like his little ID card that you use to make your laptop work, which I used to use. I mean, simple things like that kind of an
Right.
attitude. You're not in our group.
Yeah.
Yeah, it's one of the reasons I don't work at NASA.
I mean, I'll point out that there is a certain amount of science is like a brick wall. You really can't understand the top brick unless you understand the bricks beneath it. But there does come a point where you're just needlessly jargonizing things so that people can understand.
Well,
And-
and somewhere where it really shows up that's significant is you write a proposal, and scientists now mostly are so pigeonholed into a very small, narrow range in their discipline as an expert, and they write the proposal from the point of view of an expert, and yet the reviewers, the people that ultimately is going to sit in judgment of that proposal, may not know half of what this person is writing about, right? And you don't have the time. I wish we did, because I've been on these panels myself for NSF and NASA. I don't have time to run off to the internet to look up every third word in a proposal when I have to read 30 of them in a couple of days, right, in detail.
Makes me feel better. Thank you.
Yeah. And so what do you do? And then from the point of
It's
view,
tough.
if you're a program director and you want to select people to be on the panel, how are you going to find somebody who's so specific as an expert as that person who's writing? You're not going to do it. You're going to run out of panelists
people.
quickly, right?
Yeah.
And I know we're talking about inside baseball, folks, but there's also something called conflict of interest. So
Right.
ironically, if in having someone who's an expert on your field, if you happen to work with that person, they can't review. You have to declare that you're not a conflict of interest.
And then at the same time, if they're in a competing group
That's
with
also-
you,
yeah,
I
they
don't
also-
want them reviewing anything.
They also look for that too. You can even mention, I don't want so-and-so to read my proposal.
I can give you a specific example about that. Remember when one of the first gravitational wave sources that were detected, everybody was running to their telescopes to look for EM signature from it. And there's the first detection. And it's like almost anybody anywhere in the world, almost, that were involved in any type of major observatory, right? We're on
Everybody
that
was
paper, right? So who would review it?
Right.
I love that. I mean, I'm not even an expert. I'm very much not an expert in the field, but I like looking at that paper because of the author list.
Yeah. It reminded me of
For those who don't know, yeah, the author list was your arm long, if not longer.
Now, the first paper I seen like that, this is also going to date me, is the discovery of the top quark from Fermilab. That had a huge number of authors on that paper, and I remember as a young student laughing about that. It's like I could close my eyes and just pick a random person from that list, call them up and say, what did you actually do on that paper, by the way? well, I swept the floors that night, you know.
Yeah,
Yeah, so it's kind of weird.
That's become an issue, and that's become an issue with radial velocity observations. We need to make sure to include all the students who take the data.
Well, now I can just discuss a little bit on the other side of this, because it is important as from a student perspective. As you know yourself, as a student, you want to be on research papers. If your ultimate job is to get a postdoc and then a faculty position, let's say. And so you could have a CV, so your resume, in other words, could have, I don't know, 25 papers on it by the time you enter your first postdoc. And someone would look at it and say, my God, you are a super person. You are so productive. But when they look at them in detail, you're the nth author, right? Because you're on these large collaborations. And what did you really do? And in the past, I know people argue, oh, you have to be the first author and stuff. It doesn't work that way nowadays. A lot of people do have hundreds of papers now because they're just part of these large collaborations, and they're spitting out, more than 50 papers a year in some of these big projects. So what does it really mean now? And to judge if you're the first, second, or third, or nth author on these papers where they're so huge, and it really kind of smears out that understanding, at least from my point of view.
Right. But
Yeah, that is true and hard to judge.
and I'm going to ask a question. You said you have students collecting data on radial velocity. You actually have undergraduate students collecting such data?
Well, so it's mostly being run. It's for the graduate student's thesis.
Okay.
But right now we're still kind of getting our footing. So I'm thinking, because it's all remote. So I just asked my undergrad students if they wanted to come to the house and watch us. Sorry, it's my beagle. Wanted to watch us observe at the telescope remotely. So yeah, I will have undergrads, and they can do stuff like take the logs, and we'll put them on the papers. I mean, it definitely, whenever you have 20 people on a paper, it doesn't hurt to add another student.
Right.
I mean, give them credit for taking logs. I mean, it's better than leaving them off.
Right. No, I get it. So.
Yeah, it's also nice to see where the data actually comes from.
Right.
So to get involved and know that whole process, right?
They realize that observing is actually kind of boring.
Yeah, well, the thing about observing remotely, of course, is the fact that I love when I go to telescopes, and one of the first thing I do once we're ready to roll is to get a good idea what the sky is like just before it gets dark.
Oh,
Right.
yeah.
I
tend not
yeah.
I used to tell my students that astronomy, get used to it, because they'd complain for the observations we'd require them to come out for. They'd complain about it being cold, and I would have to point out to them, astronomy is done in the dark and the cold, folks.
Well, actually, at major observatories, we're in a nice heated room, right? It's
Right.
not cold.
That's
So,
true.
yeah.
That's true.
So don't really worry about that part of things.
Things
Right.
have definitely changed. We're not getting to go to the telescopes anymore, which is kind of sad.
It's
'cause I find
sad.
that the best part of what we do.
Yeah, and also for students, at least when you get a new student, I think a student should go there at least one time,
Yeah,
right?
I've not been able to take my grad student to a telescope. Yeah, we just haven't. We've gotten lots of telescope time, but we're not physically going to the telescope.
Yeah, and that is a shame. They should have the setup, at least for the major observatories that can afford it, allow you even to pay you to send your student there, at least for the first run. And if you go back again, well, then I can see doing that remotely type of thing, right? So,
Major observatories that can't afford it. I laughed at that.
well, I was thinking that, the old.
Are there any anymore?
There are. You think of what Noir, so the old NOAO that's now.
Yeah, but Kit
They
Peak
s-
doesn't necessarily have the money.
Yeah, but
Well,
they still support graduate students to go there. If it's
Oh,
part of their thesis, they will pay for the
Okay.
flight and for the accommodation. So they still do that.
I,
And I know CTIO, right? When I use the camera there, the dark energy survey camera, DCAM, you have to go there at least once to use it, and then you can do Q observing.
okay.
Makes sense.
Yeah, and
Does make
that's
sense.
yeah, and I think if we can support that, whether it's NSF that ultimately supports it or whatever, I think that's a good thing because it really shows you what's going on with the instrument.
Well, I'm just going to say I'm jealous anyway, because I've never been on a major observing run like that myself. So,
Bring you eventually. I'm so spoiled. I have not been to Hawaii in all of 2 or 3 years. But
Right.
my thesis advisor was Andrea Ghez, and we observed the Galactic Center. She won the Nobel Prize for it. And she used to make a point of definitely, I don't know if they do now, because now it's all remote, but she always did like to go to the telescope to talk to the instrument people and, you know, interact with the scientists. And also it's a quiet place for us to do our research too.
Yeah,
Right.
and that's the Keck,
Distraction.
right, and that's the Keck telescope you're referring to.
Yeah, sorry, yes.
Yeah, and so the other thing too is don't forget if you bring a student and you wonder, you know, one of the things I was told, because not told, I read about when I was young in high school was it takes a lot of motivation to get through undergrad to ultimately get to the point where you're enjoying the life as an astronomer. So what better way to motivate somebody than to take them to the Keck telescope? Think about that.
Right.
Right? And
It's also a good way to motivate a donor too.
Yes, and you would lose all of that if they don't get to go to the telescope, the student, right? So
I've told students that too. Every now and then, no matter what you're doing, you've got to do something to remind yourself why you thought it was cool and neat in the first place.
right.
Because otherwise you get destroyed and broken down by it, you know.
Right.
So
You can
and
walk
it-
outside, look at the stars.
that's it. And on that note, I've got to say it's time to start wrapping up.
Well,
So
that hour went quick.
that hour did go quick.
Sorry about the dogs starting to get crazy.
Well,
My girls get old and cranky, like me.
Okay, well, first of all, thank you very much for doing this.
Thank you for doing it.
And
You.
the other thing is, at the end of every podcast, we always say a quote. This time, I usually I say the person and then I read the quote. I'm going to go backwards. I'm going to read the quote and then at the end I'll say the person, and you'll
Okay.
understand why here in a second. So I've tried to pick something that's maybe related to something we talk about today. So here's the quote: "The only thing that scares me more than space aliens is the idea that there aren't any space aliens.
I've heard this
We
one.
can't be the best that creation has to offer. I pray we're not all there is. If so, we're in big trouble."
You're starting to sound like him. You're doing a good job.
Who do you think said that?
I can't remember who said that. I've heard that quote
Sounds like a
though.
Michiko.
No, the person who said it, Alan DeGeneres.
Ah, Ellen.
Generous.
Okay,
Yeah.
interesting.
I don't know who that is. Who is that?
Talk show host and
Yeah.
comedian.
Oh, okay.
Yeah.
So,
Anyways, for those of you who are listening, if you're interested in science, if you're in any STEM field or in the arts, as we mentioned already, humanities, I mean, please consider higher education, taking online courses if you have to. Better experience, of course, is to be on campus.
right?
Be able to see Robert and I, for example. But
Come see us.
welcome, join us here at the University of North Dakota. And if that doesn't work, maybe you can go to Mississippi State University.
Absolutely. Great place. I will say that.
Yeah, there you go.
Definitely different weather.
Yes.
For sure. But our next podcast will be next Tuesday, October the 24th at 3 p.m. Central Daylight Time. And for now, thank you very much for listening and
Thank you for
watching.
listening.
Don't forget to give us a thumb up and subscribe if you haven't already.
Yep. All right. Have a good evening, folks.